I wonder where Dan went. He was here earlier. Not that cool. Well, we're not that serious.
No, I'm just trying to be safe. I mean, these are actually really good ones. So they have the extra capacity in loops. So they basically have essentially no discharge property. We'll need to get some replacement clips.
What was that?
We'll need to get some replacement.
Oh yeah. So what was the clip that was left on it?
No, it was just broke. It just broke into pieces.
Well, I think I might not be able to come in tomorrow. I just found out tomorrow morning.
Okay, that's okay. I mean, I'm usually okay.
Yeah.
So if you have a problem, then broke off.
It'll be fine. There's
No, I think just broke off. Oh, it's a little bit extra.
I don't know.
If you want, just now. I'll go get it. Okay, yeah, I'll just come down and I'll give it to you here. But let's see, before they do that, do you want one board right on this board?
Yeah, please.
No,
I mean, what this?
One right on that.
Maybe 10 minutes to get it out.
Actually,
No,
lights are getting like.
That's
we
okay.
go out from this building. We go to our hotel. And so we first we found the drama theater.
All right, so.
Just
Then it's a bit
yeah. That's it.
That was the day. Yeah.
Oh, well, the one is fine, but
Yeah.
it's just
In the middle of the day, there is an empty, I think there is but that was for the basement.
Can you also tell me where the edge of the door is?
Just the one like that. This one.
A little bit right.
Here?
Yeah, that.
This one is really cool.
Rich, can you check whether the gain is okay?
Yes,
Can you
the
talk a bit
microphone
more?
is okay.
This is for possible.
Dan, don't do touch forward. So here's how you should do it.
Oh, we went to push start. It's in the spot. No, push start. Oh.
Oh, you want the mirror? You do that too instead.
So what happens? Now we can show some of this stuff.
So then I would just mirror your displays and normal. So
Just looking for the few one
minimize that and drag it over to the screen.
So do the second.
Yeah, duplicate will do. It should.
So just the first 2 minutes. Yeah, just do this.
Yeah.
And then we can do the
Yeah. I mean, whichever way. Yeah.
Now extend or
Well, no, I can actually play it back. Just at least because maybe sometimes when you make full screen, it will do it. No, it's built full screen. Okay, it works. Yeah. Okay. Okay, cool.
And then you can extend.
Yeah, but you want to stop the full screen first. Otherwise, you're probably going to get confused.
Two important things about right?
Yeah.
So first of all, this is the actual line. So these are the actual end of the video.
Okay.
If you don't go,
Basically, everything to the right of
Only secrets for the audience.
yeah. Keep the board that in here. Secondly, also very important.
Yeah.
When you finish, so start with this first one. When you finish with this one, move it down, not up, because when you move it up, it'll shade. Start just with the this is in order
Move it down?
sequentially. No, move it down and write the next one here. So
Well, it's alcohol.
it's very awkward because you have to then.
So every time I agree.
No, actually, here's the thing that happens.
What did you do?
Well, okay. Okay, so here's the light. Here's one board. Here's the stage, and below that there's the other one. So in other words, if you push this up, you want to push it up real well, because otherwise, well,
What is the order? This one?
any order is fine. Just you might as well shade. Basically, because anything that's in the shade will not be very visible.
So what you can do is just move this one down and then move the other one up and right, like have this down all the way down to the bottom and then right up. And it's kind of awkward because you can't quite reach that high, but just.
Oh, we tried what's like here.
No, so
Right now.
Yeah, that's very good. So you're gonna write on this board, okay? Write this board.
Right?
Fill it all up. Yeah, it's full. Now you move it down. Down. You write on this board.
No problem.
Okay?
Yeah.
So now you move this one down. And you write on this board. Don't ever move them up because even though it's much nicer for showing all your stuff, it makes them.
Okay, so this is just a movie that I tried to show you yesterday. What we're trying to do now with robots and concepts. So we have this robot, and we're trying to do some sport, like skiing in this case. Go, go, go. Go to follow. This is just a marketing movie. There's still millions of Kickstarter companies that try to do this, but we hope to have the best one. And I think at some point they remove the robot and you just see people doing extreme sports. So maybe if I ride the robot, I can also do these amazing things. If you want to get into the commercial. Anyway, let's go to our courses. So, the marketing session. And okay, so today we start to move from the intuition to the theory. And begin with a simple example. So we have a moving person, in this case is me, and the GPS data of the person. So what you see here is me moving in Cambridge. This is the three-dimensional signal. So time, and then XY. So it's three-dimensional image, and this is just a projection on XY. And we have two problems. This is the first problem with the iDiary project. When I move, even if I go to the same speed, see there is noise because of the GPS, for example. Noise that doesn't go with my movement. A more important problem we'll talk about later is that every time I go from home to MIT, it looks like a different segment, but all these are actually the same road. Maybe I use different lane, but so we want to smooth these segments, and then a harder problem to cluster these lines if it's the same lane. So this gives the motivation for the following problem, which is kind of a realization of linear regression. You have endpoints in the dimensional space, actually signal over time. And for each time unit, you have a point in the dimensional space. In our case, x and y. And you believe that all these points are lying on a few segments. You want to feed these points to k segments. So if you k equal 1, you just want to find a linear regression, the line that minimizes the sum square distance of the points. More generally, you want some k piece of linear function, which means just k segments that will minimize the sum square distance of the point. So if this is the original point, this is the projection on the k segment. So the cost, the fitting cost, is the distance between the point and its projection. And the overall cost for all the points, so the suggestion function, is just the sum of square distance for each point in time t, with its projection on the k segments in time t squared. Very much about problem, minus of heuristics over time, but we want some provable result. And again, we want it in the big data model using millions of computers and infinite number of points that come in the streaming fashion. So for this problem, we want to before we define process, we need to define some kind of query space and input. So the input to our problem is just a signal. We dimensional signal over time. The family of queries that we want to approximate the only candidate solution, in this case, is every k segment all the time, all the possible sets of k segments in RD. And we need the cost function. This is the third thing that we need to define a process. In this case, the cost for a given query is the sum of square distances of the points to the query, to the k segments. So we have the definition input, query, and output. So now we need to define a process. So I suggest, for example, this definition of process. So suppose that one perception of process for k segment queries mean that it's a weighted set. So every point in P also have a weight, and it's a subset of P. And for every k segment that you give me, the sum of square distances from the points to the segments, we approximated the same as the cost for the cost of points. But each point in the cost have a weight, so it may represent a lot of points. So you have minus point here, you just replace it by 1 point with weighting. This is the intuition. So for example, if suppose that I give you the input today and the query tomorrow. So you can compute the sum of square distance in all of n time. Just go of each point, compute the distance to the projection after all of n or all of n d time. You can compute this cost. And the motivation, for example, is that if I give you the input now, but the query only tomorrow, can you preprocess the data so that you can, for every query that I'll give you from the family of queries for every k segment, you can compute this cost in log n time, linear time. So if you have such a compression, then you can do that when I give you a query, all you need to do is compute the sum of squared weighted distance from the red points to the segments, and we're done. And you know that we have one perception approximation, but it will take you significantly less time. Now, actually, all the courses that we do in this class and all the courses I implement are essentially take a huge amount of time to compute, say n to the 5, and offline, on computer, non-parallel, non-streaming, just meta code, which is exactly the opposite of what I promised in the big data model. It will be streaming data and parallel and everything. But what I want to show you now, that if you know how to compute such a process on one computer, then you can solve the original problem on the big data model that I defined between streaming and parallel. And I want to show you that this is true for any course set under the definition that we'll define soon, but let's see why. So suppose that this is our course set. All you know to do is compress n points 1 over epsilon time into the 5 in one computer. So now I give you a minus of points and ask you for a process of this point. So you take the first set, only 2 over epsilon, and compress it to 1 over epsilon. So your algorithm is slow, but since this is such a small set, you can still compute it 2 over epsilon to the 5 because n is just equal to 2 over epsilon. So you compute the first set. But you have again billions of points on the line. Now you take the next set of 2 over epsilon point, compress it, and you have another minus epsilon coset for this set. Now the problem is that if you continue, eventually you have millions of coset in memory, and the memory will explode. So the trick is to take these cosets and take the union of these cosets. So for every case segment, this coset represents the original data, and this coset represents the original data. Think that if you take the union of these two subsets, for every case segment that you give me, I can just use the union of the two cosets to approximate the sum of co-distances from the original point to the case segment. In other words, if you take the union of two cosets, we get another coset. The approximation error is the same, right? If you had 3% milk with 3% milk, you combine, you still have 3% fat milk, but just a bit more, double than you have in the beginning. But the approximation will be essentially the same. So, and again, we just took 1 over epsilon here, 1 over epsilon here, and compressed it, and just merged it to 2 over epsilon points. But then, you can get rid of the original set, and you have only 1 over epsilon, only 2 over epsilon points here. And then we compress this coset again. So we take the union of these two cosets and compute cosets for the union. So this is before it was a merge step, now it's the reduce step. So we have 2 over epsilon weighted points from these two sets, and we apply the coset again, and what you get is 1 plus epsilon coset for the 1 plus epsilon coset that we have in the original data. So if you give me case segments, and you compute the cost of this new coset now, what will be the error, the approximation error? So what is this coset? What is the error of the new coset? So we took two cosets. Each coset was 1 plus epsilon approximation for every query. We combine it, we merge them, so we still have 1 plus epsilon approximation error. But then you compute another coset. So 1 plus epsilon coset for 1 plus epsilon coset, what kind of coset did we get? 2. Not 2. So 1 plus epsilon approximation for 1 plus epsilon approximation is 1 plus epsilon squared. Right? It's an approximation of approximation. So we have 1 plus epsilon squared coset, but we have one set of 1 over epsilon points in memory, and that's all. Now we give me the next set of points from the stream, and you compute cost for this set. And now if you give me case segment, it's asked, what is the cost for this case segment? We just take the union of these two costs. This cost will approximate the distance from these two sets. And this cost will approximate just the distance of its own set of points. And again, we have another set, compute the cost for it. Merge into two cosets to get another 1 plus epsilon of coset for these two sets. Compute another coset and get 1 plus epsilon squared coset. The problem is that if you continue in this way, again, we have too many cosets in the second level. What do we do? Yes. Another one, right? We just compute another coset for these two. Just merge these two cosets and delete them from memory. Now compute 1 plus epsilon approximation. And it has 1 plus epsilon to the 3 coset for all the original data. So in the worst case, how many cosets we will have in memory? So if you have n points, 1 coset even in the leaves. How many cosets? For example, now we have only 1 coset, but before we have 2 cosets. Also here we have 4 cosets, or like this 2 cosets. What is the maximum? If you have n in general, this was a small binary tree. If you have in the leaves, n original points, how many cosets will have most in any given moment?
Log n.
Log n. Why?
The depth of the tree.
Excuse me?
The depth of your tree.
The depth of the tree log n, so what?
So every time you're doing the depth of the tree, you're merging 2 at a time.
Yeah, the turbo version. First, if you have binary tree, the depth is log n. Second, you have most 1 coset in each level. Why? Because if you have two courses, you immediately delete them. That's why we have just log n courses. And each course is small, is log n multiplied by 1 over epsilon. Another observation is that even if I have n equal billions, I still never run the algorithm, the course algorithm that I write in MATLAB or Python, on the millions of points. I only run during all this process. I run the algorithm only. The input was 2 over epsilon, the output was 1 over epsilon. The input was 2 over epsilon, the output was 1 over epsilon, and the same is the next level. That's it. Only with two routines that I apply. Take sort of very small set of points and reduce it by half. I never need to run a large data sets. This algorithm, and this solves the streaming problem. So I can continue this and have only log n set in memory if I solve only n points till now. So a question, some people ask me, why can't I have a set of points, you give me new points, I just add them to the core set and compress. Then you give me another set, I take the union and compress. Why can't I can't just do this? Why do I need this tree? Every time you give me a set, I can just add and compress. Add and compress. Not really need the tree. Why still use the tree? What's the problem with this approach? Take the next 2 points, just merge them and compress. Take the next point or 10 points, merge and compress. You want to see the problem? Yeah?
Your power would grow linearly in the number of partitions.
So remember here we paid, this was 1 plus epsilon cost, this was 1 plus epsilon squared, this was 1 plus epsilon to the 3, and if we do it n times, it's 1 plus epsilon to the n, which is pull out to 1 plus epsilon n or something like this. But if you use this tree, eventually we have 1 plus epsilon to the log n, and how big is this? This is approximately, any guess?
1 plus log n epsilon.
The buffer, yeah.
2.
1 plus, okay. Some points. So, which means that if you just run the algorithm with epsilon over log n instead of epsilon, you still get epsilon approximation. So this is a small number, this log n. So it's very easy to replace epsilon by epsilon over log n, you still get a small process. So when you actually, this is for real one, when I actually look at the memory of the computer, we see that this is how it looks. This is for real one, and all these jumps, of course, are because of the way that we construct the tree. So sometimes we add a point and we do nothing. And sometimes we add a point and we need to update all the log n levels. So this is the size of the input, how many points we inserted in the stream. This is the memory. Just when we write the method, how much memory I used. You see a beautiful log function here. And then increase more and more points. There is now, okay, we're talking about streaming. How about parallel computation? So how can you compute this tree in parallel if you have a lot of computers? Any suggestions? It's very easy.
Inversely parallel?
Can you hear?
Inversely parallel?
Yeah, inversely parallel. What does this mean?
Mean taking 2 nodes and merging them at a time?
Yeah, I mean, this concepts are independent. So the case segment mean you cannot solve the optimal solution if you just have this set. You cannot solve the case segment mean here, the case segment mean here, and just combine the solution. But for causes, you can do this. So you can compute the causes for this set and this set and this set and this is totally independently. At the same time, simultaneously, then take the union and then compute the next level, and then the next level. So in the end of the day, so all the night we run compression for the huge amount of data, and in the morning we just take this small compression and run the heuristic or the algorithm on the small compression. So again, it's totally different from what we used to do. So most of the time we spend on compression the data, and in the morning, just use one computer and one meta function to compute the courses for the optimal solution on the small courses. So it usually takes just a minute when all the night was spent for compressing the data. The problem with this approach, and it's very easy, by the way, to implement, for example, using Hadoop or MapReduce. We just say this is 1 and this is 1, this is 2 and this is 2. And then for the mapping, this computer gets the first 1, this computer gets the first with level 2, and then they reduce the data again. We just do 3 iterations in Hadoop, and it's straightforward to implement this using Hadoop. The main problem is that here, we have parallel, but we don't have streaming data, right? So here I assume that you have all the data and just split it into different computers. But before I assume that you have one computer and you get the data on the fly. But what if you have infinite stream and you still want one pass over the data and you still want to use the 10 or 100 computers that we have on Amazon Cloud, for example? So this is a bit harder, but do you have any idea how we can combine the parallel and streaming? So we cannot just take the courses and split them because this way of infinite courses, infinite number of points, just writing, and you still want to use a lot of computers. So we solved the problem with one computer in the streaming. I told you what to do when you get a few set of points, just compress them into the tree. But how can you do this if we have 10 computers or 2 computers? How can you take advantage when you want to divide the time by half? So this is the trick. Just if you have 2 computers, just send the given points, the point of the given index to the second computer, and with all the indexes to the first computer. So first point goes to this. Second point, of course, goes to this computer. Third goes again to this. Fourth goes again to this. Each computer will just compute its own course tree. So each computer will just get a stream of points. This gets a stream of green courses. This computer will get a stream of pink courses. Each one will compute the stream independently. In every given moment, when you have course of all the points that we see here now, you just ask for each server or computer to give you the courses in its tree, and then the union, and again you have course of all the data. The main problem is actually we don't have a concept for this problem. So we can easily see, give an example where every course that you compute for the set of points for the k-segment problem must have at least n of size, well, must be of size at least n, which is the size of the original data. This is for one example. So for example, assume that this is P, this is the input. And you say that you have small weighted subset, say n minus 2 even. I give you n minus 2 points to choose. You choose n minus 2 subset, give them weights, and say that for every k-segment that I'll give you, you have good approximation for the cost, the sum of square distances. So suppose that you take all the points except this one. And I want to prove that you actually don't have a cost, no matter which way to give these points. How can we do this? I want to give a query such that the fact that you didn't take this point will prove that you don't have a cost. And again, context must be good for all the possible queries in our family, for every case segment. Any suggestion? How the query will make this point extremely sensitive and important for computing the cost function? We just choose a query where the cost of the query is dominated by this point. If you didn't take this point to your concept and I give you, after you give me the concept, I give you this signal, so what will happen is that the function that I gave you cover all the points except this one. The original cost is more than 0, but no matter what weight you choose for this point, the cost for the concept will be 0, because you don't know about this point. Which means that no matter how small or large epsilon is, you have a very good approximation. You want multiplicative approximation, and if you answer 0 when the real answer is more than 0, you don't have any constant factor approximation for every constant, non-constant number. So it's a pity we have a great idea how to use the courses in the tree in big data, but we don't have such courses for the problem. We don't have great subset. But look again on the slides, all the tree that involve raises. Yeah. When I tell you all this story about the compression and manage and reduce, I never detect the course that is a subset or not subset. question is what? The minimal assumption, what should be the course definition so these tricks would work on the course set? So first of all, I'll show you why we can have good courses for this problem if we just change the definition. For example, in this specific set that I showed you, there is no course set, you can trivially just take the first point and the last point. And since the distance is the same for each pair, for every case segment that I give you, you can just run the integral and compute the sum square distance for the point. In some sense, these two endpoints represent all the signal. Even if you have minus a point here, we don't care. We just need the two endpoints, and you have point of zero error. The only problem is that the definition, the way that you use the course, you just take the sum of square distance from these 2 points, and you run some integral of the sum of all the points in between. But these 2 points represent exactly the original input. And the same if all the data is contained in just 3 segments, you can just take the endpoint of these segments, and this endpoint represents all the data. And here you use the fact that the time, unit time, is constant. So when you have 2 endpoints, you know exactly what happened in between them. And if you have just k segment, you can have such a compression of 2k points, and we're done. Of course, in practice, data is not in k segments. So the concept that we were able to construct, and I hope to show you in the next days, is that if you project all the points on a specific set of k segments, and you choose some representatives that are very far from these segments, what you get is actually more points that you have here, because you have n projected points and few 1/epsilon points outside. So the size of the course is actually larger than the original data, it's n plus 1/epsilon. But all these endpoints can be represented by the edge, so all these endpoints will be represented just by 2k points. And the trick is for the cost function, you use the cost that will be different than the original cost. So this is giving intuition why for every paper we need to define a new cost, because we see that the definition doesn't work and we have a new definition for the very specific problem at hand. This was just one example. So I tried to write down what are the minimum properties that we need for the cost definition. So all these tricks for the big data and the streaming in parallel would work. And that's why we need the first formal definition. So X in our problem is just RD. So this is for the K segment mean problem. K segment first. So the input, we have points in RD. But in general, X can be a set of chairs, bottle of beers, lines, bottle vector machines, whatever you like. And so all I know about X is it's a set. The next thing, we need a set of queries. What models we're trying to fit for the data. So just another step. Usually, both of these data are infinite size. This is all the points in RD. This is all the possible K segments. So Q or possible K segment, which means take these are linear functions. So Q is all the possible, the set of all possible K segments, but in general, again, is just another infinite set. And we need a cost function. What exactly we want to approximate? So the cost function, get a subset of the space. Okay, specific signal, for example. So this is how we know the subset from X. And you also get a query. And the output is just non-negative number. we want a negative number because if it will be negative number, it will be very hard to talk about from perception of estimations, strange things will happen. So we just talk about positive cost. And now we can define what is the cost for this problem. So we have cost function queries in one set. And we say that so we give an epsilon, which is the error parameter, and we are given some subset that we want to compute cost for. This is a specific signal in our case. P is the GPS points. In this specific case, and what we want is a cost set, which means that for every possible query in the family, so remember there are infinite number of queries, but still for each of the queries, we want that the cost is 1 plus epsilon the original cost of the query. So for every query, the cost that you get from the cost of this query is plus 1 plus epsilon the original cost, and more than 1 minus epsilon the original cost. Another way to write this, sometimes it's more simpler, is to say that the cost Q minus cost, the cost of the Q, absolute value, is epsilon cost PQ. So this is the same, these two. So if you take the difference, you get epsilon compared to the real value that you want to compute for the original data. Okay, so we have cost definition, so what now? Now in order to actually apply it for the streaming tree, for the emerging reduced tree, actually down, right? Yeah, cool. Right. So now we need a theorem. What can we do with this? So suppose for every P1 and P2, so the property that we want is given two core sets, compress them again to a new core set, the same size. That's actually the only property that they use in all these stories and animation that they show you. So for every two sets of core sets actually that we get in the tree, we assume that the size is these are the two nodes, and this is the size of the core set. That's why we need a small core set. I mean, of course, you can hold the endpoint and say this is a core set, but we wanted this number, the size of the core set could be small. So this is the minimum number that you can actually compress the data by half. And suppose that we can do this, so we can compute core set C Now we have the definition for the course. This is the definition for the first slide, for the previous slide. So this is well defined. The size should be the same because we want to shrink every 2. We want to shrink every 2 to another course with the same size. And we want to use X memory. Yeah, there's something. Yeah, accurate. Let's just keep it C. So we can do this using OS memory, using also C, and what's important is the time. So this T might be quite slow, but we don't care. And we assume that this is what we can do in one machine using your Python code, and that's all. Now we have the then. Essentially, what I want to say is that we can have this magical tree, imaginary tree that I show you using this course. So the data is now streaming, so I said we can maintain, but the data is keep arriving. Course set for the endpoints. The endpoints that we got to now. So n is changing every time that you get new point. N is increasing. Endpoints in so far. And we also want parallel algorithm. So we want to take advantage of machines. Instead of machines, we can talk about threads. So one machine with several threads is also okay. And the insertion point, the insertion time, so it will be just log n. So we need to update it most log n core set, but each update will take at most O of t time. And it's not for one point, it's for n point. So for endpoints, what will happen? We take the next endpoints, we spread it to the M computers, and then go to the next endpoints. So every time that we take the endpoint and spread it to the M computers, everyone will be in parallel. So that's why this was the time for one machine, but if we have n machines, we can do this at the same time. We can take the next endpoints and then spread them. So that's why the running time will be divided by m if you have more computers. So it's reduced linearly with the number of computers. And regarding the memory that we need, so we have log n process in memory. So each computer will have n over n points. But so the size of the tree will be instead of log n, it will be log n over n. Each core set is of size C. So this is the size of the tree that we'll have in each computer. And we might need additional S memory to compute a single core set, so I just add this number. And this is for each machine. Questions so far? Anyone? Good. So the last interesting thing is that actually we can also support deletion. So how can we support deletion? Let's look again on the tree. So far. So we talk about insertion. What happens if suddenly I want to remove a point from here? How can we do this? Update all the tree after I remove a point. So anyone have a suggestion? Yes? So you already learned this trick in and then introduction to algorithms. Think about balanced trees. You remember balanced trees when you have to remove a point? The main observation was that in balanced binary tree, every leaf have only log n parents. When you move a point from here, this coset doesn't care, and this coset doesn't care. If you move a point from this original set of the coset. So all you need to do when you change one of the points from this coset, to update only the log n parents of this of the leaf, and you can do this in polylog n time. The problem is that to update all the leaf, I need to have all the tree in memory, including the deleted coset. So while we can support deletion, for example, if you want just a sliding window, so every time you want to add the new point and delete the last point, this could work, but unfortunately the time would be good, but we need all the tree in memory. And this is the advantage of Sketch that I hope that we have time to at least mention. That they have other problems. They're not combinatorial objects, but and they assume that X, for example, is a set of matrices, for example. But you can add a leaf point without using all the memory and remembering all the points. So I leave the proof is essentially based on the figures that I already showed you. So I expect you to prove better stuff. If you have problems, please let me know. I hope it's still true, because this was my PhD part of it. And from now on, we don't need to talk about big data or power computation or streaming. This was supposed to convince you the only thing that you should care about in life is coset. Once you get coset for small data in Python, and C is a small number, so you have coset that get 4 per epsilon and 10 1 per epsilon, will take 2,000 points to 10,000 points. Even if it's just a few lines in Metal or Python, you can go to Google and say, I have an algorithm that can take care of billions of points and units of computers in parallel. Just use this box on all these on computers and together with imaginary tools. And so the lecture, I will just talk about how to construct this coset for classic problem. Yeah.
So when you delete a point from a coset, do you just relieve it or how do you represent the coset?
Oh, this is quite straightforward. So we have some points. Yeah, I didn't draw the point, but so we have some points. This is the original point. And in the figure, I just showed the coset of these points. Okay, so you compress this point to a coset, and then you have another coset here. Now, if I delete this point, this coset might be bad, but something maybe other points will be important. So just kill it and compute this again for this set. So remove it, compute a new one, and then you take this coset and this coset. So you just delete all the original coset and just recompute them, so it shouldn't take too much time. More questions? Yes.
Excuse me, can you please clarify why the insertion time order of t log n, where does the log n come from?
Oh yeah, so let's see. So what will happen? So when you add a new point to the tree, so if you're lucky, you just have few points here, you just add them. In the worst case, you might have too many points and then you need to convert cosets.
I understood that. I thought that you were talking about when we were doing, we were having n computers. Is there anything to do with n computers or
No, the n computers come from here.
Oh, it's the same. Okay.
So actually, if you give me 1 point,
Right.
I just give it to one computer. I don't do it in parallel, right?
Okay.
So at 1 point, I don't do it in parallel. We take it at the same time. So that's why I just rephrase it like this. So I say take the endpoints and send them, and then update the trees in the same time. You just take a bunch of endpoints, and then I can say 1 point, but then it will be amortized time and blah blah blah. But I don't want to confuse you with the amortized time. So I just say for each endpoint you can do this. Of course, you can have amortized insertion time for 1 point. You can also get the n over m here or something like this. But I saw that this is a bit nicer. And that's what we do in practice. So let's start with the cosets. Again, concepts are strongly related to the problem at hand, and that's why we have so many concepts and I have so many papers. So, yeah. So we start with this simple problem, minimum closing ball. So the input is endpoints in RV as usual, exponential geometry. The query is a point. And this is under the case segment that we had before. And now the cost is what is the farthest point in the input from the query. And of course, the point that will minimize this function is the point that minimizes the sum of the maximum distance we have defined. For example, the get down, right? So for example, in the problem with the robots, we have n people with smartphones, and each smartphone will contact you several, the quadcopter or the robots, and you pay the maximum distance, the less satisfied customer. And the question is where to put, what is the optimal query? What is the query that will minimize the distance to the farthest client? But again, when you define the concept, there is no optimization problem. It's that set, it's just a set of all the candidate solutions and the cost function. When you get the concept, you can run your favorite optimization function on this, but the cost promises this. And this is important because if the concept only approximates the optimal solution, there's no such thing as optimal solution. The optimal solution will change over time when you get more and more points. We don't care about the current optimal solution of the set. We want it to be good for any possible optimal solution in the future. So that's why we need the cost will be good for every possible query. So if I give you the endpoints today and a query tomorrow, can you preprocess the data tonight so that when I give you the point, you know what is the farthest point in log n or 1 over epsilon time without going over all the points and compute all the n distances again, just because I gave you the point already yesterday. So let's start with the case d equal 1. So you have points on one-dimensional set on the line, and I give you a query tomorrow. So today I give you the point, tomorrow I give you the query. What is the farthest point from this query? Left or right? This is the farthest point. If the query was here, what is the farthest point? You have to guess what is the concept for this problem?
Median star.
Just take the two extreme points, and you don't care actually about all the points. When you give the points tonight, just do all of them, just take the two endpoints, and you have a concept, and tomorrow when I give the query, we just look which is the farthest point and give me this distance. Quite easy, right? So we have the first concept. Great. So far PQ will be the cost, the distance from Q to the farthest point in P. This is the cost essentially that we defined that before. Yeah, so you got this idea. Actually, even if the query is not on the line, and this will be important in a few minutes, the query will be here. What will be the farthest point in this query? It will be here. Still be this point, right? And the same, if the point will be on this half space, this will be the farthest point. So actually, this concept is good even if the query is in RD, not only on the line. Just assume that all the points are on the line. Take advantage of this later. It's less easy in two-dimensional space, right? You cannot use this trick because there is no linear order. So that's what we're going to do. Just choose an arbitrary point. Take the farthest point from this point, Z. So this means that the ball, farthest R, where R is this distance between them, you cover all the points, right? So you took a point, you took the farthest point, we call this R, and this is the radius, and we build a ball around them, And now we have a ball that covers all the points, right? Next thing, we construct a square, or a cube in general. So the size, each side will be 2r, because this was r. And you construct a grid. So the size of each cube in this grid, each cell will be epsilon r. So how many squares will we have? How many steps will we have in this grid?
Epsilon squared, r squared.
How many cells we have only on this side, in this column? How many cells? So this is 2r, right? Every cell is height epsilon r. So how many cells? Yes, one of epsilon here, one of epsilon here. So we have two over epsilon, 2 over epsilon. So it will eventually all of 1 over epsilon squared points. In general, all of 1 over epsilon to the d. Not too much. So now all we do is we take representative from each cell. So if you have units point here, they are represented by one point in the core set. And that's it. This is the core set. And again, the idea of using grids and clustering is well known, but we add additional tricks in the beginning to decide what is the right size of the grid so we can actually prove something about this compression. So the fact that the core set is small is straightforward. It's 1 over epsilon squared, at least when d is small. When d is large, we'll talk about it later, but currently we just d equals 2, so we have small set of points. So size of C, which is C here, is just 1 over epsilon squared, actually independent of n. Even if you have billions of blue points, you still end up with only 1 over epsilon squared points. Quite interesting. So now we want to prove that this is a core set. So what we want to claim that for any q that it will give me, if I look at the cost to P and to C, it will be approximately the same. So the cost of the farthest point from C, which is the farthest red point, and this will be the farthest blue point. We want to claim for every possible Q to be most 1 plus epsilon. Like we promise here. So cost for every C and Q will be approximated. It will be essentially the same as cost P Q and Q up to 1 plus minus epsilon. So one side is very easy. Okay. So one direction, this direction, is straightforward, and actually we don't need this 1 plus epsilon, it will be only 1. Why is this? Because C is a subset of the original point, right? So the farthest point from C to Q will be less than the farthest point from P to Q. If you take less point, the cost will be reduced. The farthest point will not be larger than the original data. So this line is straightforward. It will be much harder to prove that the cost of P to Q is less than the cost of the subset, because this is small and this is large. So why you can do this? So we need to prove that the error is epsilon. This is again, I use this equation here, which is essentially the same. We want to prove that this time the error that we get is epsilon compared to the real output that we need to give. So why this is small? So far P, the distance between P and Q is less than the distance to so we want to know what is the bound this distance from the star to this blue point. So by the triangle inequality, this distance is the smallest distance from Q to the red point, plus the distance between the red point to the blue point. This is triangle inequality. So, but we know that this distance is about epsilon r. Epsilon r squared 2, right? The maximum distance between 2 points, if the square of side length epsilon r is about O of epsilon r squared to epsilon r in 2-dimensional space. So we have this inequality that the distance to the goal point cannot be too large. And now we should want to show why this is small. So every ball that covers these 2 points, U and C, must be of size at least R. Because this is the minimum enclosing ball of these 2 points. In particular, this is Q. This is the farthest point from Q. It means that the ball, this radius, cover all the points because this is the farthest point from Q. So if this ball covers all the points, it also covers Z and U. But every ball that covers Z and U must be for the diameter at least 2R. So we get this bound. So we know that R is close twice. It's less than twice this number. So we have a bound on R. So the error from the last slide, epsilon R, is actually epsilon than the actual cost. In other words, the size of the cell is small compared to the real value that you want to approximate. So finally, the farthest point from P to Q is less than the triangle inequality, the distance from C to Q, plus the error between the red and the blue point. But this error is epsilon compared to the real value. And this is the end of the proof. So the error, the difference between PQ and phi CQ is epsilon part PQ, which is what we want to prove here. That's it, right? Quite easy. But this is actually a very easy problem. Any questions till now? Good. So now we can just, yeah.
If I have a fixed epsilon, how does my core set size grows if the dimensionality is growing?
Good questions. So you tell me. So what is the size in this case? It was epsilon over epsilon squared, two-dimensional space, right? Where did this number come from? This was the size of the grid. So it was 1 over epsilon multiplied by 1 over epsilon. In three-dimensional space, this grid will have a cube. So it will be 1 over epsilon to the 3. In d-dimensional space, 1 over epsilon to the d. Too bad for high-dimensional space, right? So we get rid of the n, but we have a problem with d. Unfortunately, we can prove that this is allowable. So for example, I give you some exercise, but if you take all the points on a unit cube, uniformly distributed on a unit cube, then you essentially must take 1 over epsilon to the d point. Otherwise, I can just put center whatever you miss the place and show you that you don't have a coset. I give you some exercise, and maybe in the last talk I'll give a reference to the solution. But the good news is that here we have a very strict demand. We want that for every query, the cost will be approximated. And the question, if you only want to approximate the optimal solution, not every query. So of course, the optimal solution keeps changing, but we want the optimal solution of the point that we see till now. Can we do better? And the answer is yes. So this is what we call a weaker cosets, and I'll talk about it probably tomorrow. So now we have this coset for 1 point, and this is a linear problem. This is a very complex problem. It's not too hard to solve, even a bit slower than this. But the problem is how we solve this for the case. So actually, before this, I want to show another trick. Yeah, blah, 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 blah. So another coset technique. If you want a coset of size only 1 over epsilon, not 1 over epsilon squared, can we do better? So this is the trick. Take a point U as before, arbitrary point, but don't take the farthest point. Construct star around U. So the star should have 1 over epsilon lines with angle about epsilon between each 2 lines. And now a very classic trick of coset construction. We project the original point, each point with closest line. So what we get, we still have endpoints, but now all the endpoints are lying on 1 over epsilon lines. to reduce the dimensionality of the point in some sense, although we still have endpoints. But this dimensional reduction, which is, again, classic idea in course construction, first let's project the point on something and then continue. Even if we still, although we still have endpoint, it will be now much easier to construct a course set because you can just take the union of the endpoints of the lines. Remember how we construct courses for one point on the line, just the two endpoints? Now we just use it. When we have points in the line, we just compute courses for one point on the line, and we know how to do this, just take the two endpoints, which was the first exercise. So we kind of reduced the two-dimensional problem to a lot of one-dimensional problem. And this is the output. So now we have only 1 over epsilon or 2 over epsilon points, not 2 over epsilon squared. But we have 1 over epsilon lines. Each line has 2 representative points in the corsets, so 2 over epsilon. So why this corset is good? This question, yeah?
Does epsilon grow as we get far away from the center?
No, epsilon is constant. It's part of the input for the system. Epsilon, K.
Just intuitively, if you get far away from the center, the distance between the points and its projection tends to...
I think the next slide will help you to understand what's going on. So why this is a corset? So suppose that we project the points, and the projected points are, we call them P prime, and we have corset for the projected points. But you can actually prove that P prime is a corset for P. So even if P prime and P have the same size, if P prime is a corset for P and C is a corset for P prime, by definition of this, the corset, the definition that we wrote here, C is a corset for P. Because it's approximation of approximation. Maybe you lose 2 epsilon instead of epsilon, but it's still a corset. So this is also related to the idea that was just yesterday, let's compute a corset for a corset. In general, it doesn't make sense. But if it's different type of corset, sometimes it makes sense. So in our case, P prime, just the projected points, all the red points and the blue points projected. And C is the red point. And we want to prove that C is a corset for P prime. So the red points are corset for the projected points. Why is this? So we consider only one set Pi, the original point. And we know that Ci is a corset for Pi. That's what we proved. This was the first exercise that I gave you. We have points, on a line, we just need the 2 endpoints and we have a corset. So now, we take the union of all the corsets, and again, by the property of the corsets, we have that the union of all the corsets is the union of the corset for the union of all the projected points. So C is a corset for P prime. And now the question why P prime is a corset for P. So we know that we approximated well the projected points, but why is it true that the projected points are a good approximation for the original point? Why are we allowed to do this projection? So let's see what's going on there. So we want to prove that the farthest point from P and P prime is approximately the same for every Q. So we need to prove this, and we again use the same. We need the same inequality that we had to prove before. And suppose that this is Q is the farthest point from P. So P is the farthest point from Q, and P prime is the projection of P on P prime. So what can we say about the difference? So again, by the triangle inequality, the error is this distance. So the distance between P and Q and the projected point to Q is at most this distance. This distance is just the distance between P and P prime. Now what can you say about the distance between this point and its projection? So the main observation is that since this angle is just epsilon, so this distance is just epsilon this distance. Okay, this is related to what we said. Even if the point is very, very far, it will be only that this one will only epsilon to this. So it will be sin alpha, but sin alpha, because alpha is epsilon, sin alpha is also about epsilon, and we have this bound on the distance between the 2 points. Now, why? So we haven't got the epsilon. Why this UP can be too large? Because this UP is less than the farthest point R that we defined before. And again, we use the same property that R is a bound for the farthest point. So we use again this property. And we replace R by the actual cost of the query. And we end up with the error that we have is just epsilon compared to the original cost of the query. And again, the other side is essentially the same. Any question till now? Yes?
But this all depends on you choosing a center point for this particular cluster. If you choose somewhere outside, then you can project everything onto epsilon angle, and then you will only have 2 points.
So again, I use the manual version here that if you take any point and the farthest point, you have 2 approximations to the optimal solution. Okay, I proved this in the first slides with the 2 balls. Just any point, the farthest point, and take a ball. Maybe not the minimum enclosing ball, but it's not twice the minimum enclosing ball. So this distance cannot be too large. This would be that it is there. This is the UTCP right now. More questions? Yes.
So, from what I understand, basically where you choose your center will have repercussions on the compression, on the number.
So we'll have different courses, but the proof should probably remain the same. That's what I just showed. So the error is that you probably get different courses, but in the end, the proof should work for any, no matter which exact point. It will be a bit harder unless we will, for the case of the problem, that we will try to solve in a few minutes. Questions? Okay, so one center is, we have course of one center, but it's really not too hard problem. Much harder problem is K center. The K center, I want to find the minimum K, the K balls of the same values to cover all the points, not just one. And then everything is much, much complicated because this is a non-convex function. We cannot use all tricks like linear programming. But the nice thing about course is because we don't try to solve the problem, just reduce the data. Moving for K equal 1 and K larger than 1 is sometimes very easy, particularly in this case. So suppose that we take the optimal solution. The K center, the minimum balls that cover all the points of the same value. So this is the optimal solution. What we can do is we can now compute the grid for each point independently for each cluster. And essentially we'll have just double the points, so 2 over epsilon, 2 over epsilon squared, but the proof will essentially be the same. I won't repeat it, but essentially you can just have a grid around this set of points, a grid around this set of points, and you're done. The problem is that we don't know how to compute the optimal solution very fast. So this is actually a hard problem. So unlike the K equal 1 case, we just take a point to the farthest point, we have the approximation. Let's figure out for the case of K center. So in this case, we can use, for example, constant factor approximation, which means that it's not the optimal cost, but it is most twice or 10 compared to the optimal cost. And that's what we already did in the case for the K equal 1 case. We don't really need an proof at optimum, we just need that R will be some constant factor approximation. Sometimes actually, so we then apply the compute some constant factor approximation and then apply the grid different sides on each cluster, and the idea and the technique is essentially the same. For the problem, actually, we cannot have even fast constant factor approximation like K-mean or for the vector machines. So we sometimes use what they call by-criteria approximation. By-criteria approximation means that not only the cost is constant factor approximation, the optimal solution, but to actually use more than k-center. So we still compute with the opt of the k-centers, but instead use, for example, k-log n centers. And again, as long as the cost is not too large, it's still 1 over epsilon, we have log n over epsilon points, because we have 1 over epsilon for each cluster. So we pay something because of this log n, but it's not too much, just log n. And sometimes by-criteria approximation, unlike constant factor approximation, are very easy to compute. And again, after we have the by-criteria approximation, we compute these clusters for each set of points. But I want to show you something quite surprising. So suppose now we want to implement this cost construction. So there's something that we need to be careful about. So I say first a few words about implementation of this kind of process. So one problem that they have, let's go again. One problem that, for example, when I ask a student to implement these courses, and I've seen one of the blog on the internet, someone complained like these courses are so slow. This was one of the, I think we couldn't find exactly these courses in the literature, but courses for case center are more complicated. You can find people complain that are too slow because, for example, what people try to do is, for example, okay, for one, you actually construct a grid. And you just take representative for each cell. And the student complain that it's too slow. It says, suppose that you just had 20 points and put epsilon large enough, so you just did two points or something like this. Is it still too slow? And the answer was yes, it's still too slow. Because why? Because, for example, 1 over epsilon to the d quite large and it takes a lot of time to compute this. But actually, the running time should never be more than O of n for computing the course. Why is this? Why? You don't actually need to construct all these billions of cells. So, and this is in general true for all the paper. Never implement algorithm as it's written in the paper. Because in this case, suppose that you have only a few points, and you want, again, most of the cells are empty, and you want one representative for each cell. How we can compute this cost in offline time, even if you have billions of cells? And the idea, I mean, do we really need to compute all the cells, and then throw the points, and then go over all of the non-empty cells, and then compute the representative? Do you have a better idea? Yeah?
You can use dictionary modular division.
Excuse me, dictionary?
Yeah, just to store everything.
What do you mean by dictionary?
Like hash table.
Exactly. So you actually don't even need hash table. You just use the floor function. So suppose that this is 1, this is 100. Okay? And I give you a point which x value is 45.6. You know exactly by using the for function which cell it will be. So just using log and for function, you can actually detect the right cell and then store the list of the point that you store on the grid without actually computing this cell. This is an example of things that we don't bother to write in the paper and the proofs, but if you actually want to implement it, of course, this is the way that you should do things. Other thing regarding implementation is that after we, usually when you actually compute now, if you want to solve the case center on the course set, you can just run existing heuristic on the course set. You don't need to actually solve the exhaustive using exhaustive search. Probably if you just run heuristic on the course set, and so I already showed you, sometimes get much better result on the course set. And quite surprisingly, but sometimes we run true approximation, on 1 plus epsilon coset, which is a big strain because theoretically the error is 2 plus epsilon. So the epsilon current doesn't help, we just use epsilon equal 1. But in practice, don't forget this is just the upper bound on the error. In practice, we get much, much better results. And it makes sense actually to run constant factor approximation on epsilon coset. And when we decrease the epsilon, we get better and better results over time. The other observation is that, and we have it for robots. For example, when we want to compute, we have only 20 points or 20 robots, 20 people, and we want to find 2 centers. What happened if you can try to reduce this 20 point to 10 points? So in practice, we never have epsilon as input. So in practice, what we have in the code, we just tell me how much point you want to get back, and that's what I return. So and then you compute the error, and this will be the epsilon. So epsilon is kind of the output, not the input. The input is how much point you want to get back. And I'll do the best that I can. We don't really use this area in the algorithm. We just use it for for example, what is the dependence of our D? Someone asks you, and you know that when D is larger, we'll probably need more and more points. But in practice, we just compute the grid based on the number of points the user wants, and then compute the cost for this set. So again, this is very different from the theoretical theorem. And in particular, we sometimes compute 20 points to 10 points, which is from O of 1 to O of 1. It doesn't make sense in theory. In practice, works great. Because again, the theoretical bound, just upper bound, sometimes very pessimistic for any general set. Sometimes we have properties, nice fraction of the set, and we don't need all this. And the resulting practice are much, much better than theoretical guarantees. Anything else? Yeah, there is strange thing. People send me emails, use your course set to work great for our problem, and ask what is the problem, and they say, I don't know, suppose a vector machine or some strange problem that has nothing to do with the course that they use, but it still works great. So intuitively, the idea of cluster points that are near each other to oneself makes sense for a lot of applications. So I won't be surprised if you take this simple construction, run it for your problem, and you still probably get a very good approximation. Okay, so sometimes we just manage a lot of process to get heuristically good compression of the data, and it works quite well. And again, we try to use Corsair that is similar in some sense to our problem, but in practice you can use the Corsair for one problem to a totally different problem. Another one about implementations. So a good example is, for example, the Chernoff-Hofling bound. We say that if you take random sample of this size, you get 1 plus F approximation with this probability. In practice, we just sample S point. This is the input from the user. We output the approximation and how the error change when you take more and more points, and we don't give epsilon nor delta as the input for the algorithm. We just compute the distribution of the error when you add more and more points, and already discussed the last point about the implementation. The next thing I want to do is actually show you that you don't need, if you want Corsair for case center, you can just download from the internet, for example, the approximation algorithm for case center, which is well known, and then just run it with K over epsilon, or K over epsilon squared, and get the Corsair. So actually, all we did from now with the proof was just for the theory, for the theoretical proof. In practice, I want to show you that all we need is a constant factor approximation for the K-center problem, and use K over epsilon instead of K, and you get the Corsair. And I'll write the proof formally now. Probably, I'm going to erase this. So I want to show that essentially, if you have constant factor approximation for the case-centered problem, you have a Corsair for the case-centered problem. And actually, we saw this phenomenon for a lot of other related problems and Corsairs. And I'll try to write a general theorem for when you can just use constant factor approximation to turn it into Corsairs. Okay. So suppose, okay, try to write very hard. So suppose that we have coset. We just showed that you can have a coset of size k over epsilon to the d for the k-center problem. Why you just can use the optimal solution for the k-center and put 1 over epsilon squared grid for each cluster. And I want to say that if you have, I want to claim that if you just compute the C-center, I call it C star of P. So instead of K-center, you just compute the K over epsilon to the D-center. And I want to claim that this is the coset. So if you want to coset for the problem, you have good approximation algorithm, just try to run the approximation algorithm with larger input of value k of the complexity of your model, and there is a good chance that you can also apply the theorem for your problem. So why is this true? So we know that the cost of the optimal solution, the C-center, to Q is less than the cost PQ. Why is this true? So one side is trivial again. For every query Q, so now Q is K point in RD. So why the cost of C star to Q is less than the cost of all the set of points to the query? What would you use this trick? Or is this straightforward? So the cost is the farthest point from the original data to the farthest point from the center. So each point in P goes to the new center in Q. Why this is less than this?
Subset.
Subset, again, C star is a subset of P. If you have less point, the farthest point must be smaller. And again, of course, this is a subset, not just a small subset, also a subset. So this must be smaller than this. So one side of the definition of coset is straightforward. But what about the other side? So now we observe that cost PQ is less than cost PC star plus cost C star Q. So now I want to bound the other side. Why cost PQ is less than the cost from P to the maximum distance between the cost distance between a point in P to C star plus the cost from C star to Q. This is just a triangle inequality. So this is by the triangle inequality that you already used before. And it's also a common tool in coset. Intuitively, if we have 2 points that are very close to each other, they should probably be compressed and have one representative in the coset. So we have this property, and we also have this inequality. So cost P C star is less than cost PC. So C is the original coset. Why is this true? So C is the coset that we have here that we don't know how to construct. It's based on the optimal solution. But this is true because C star is the optimal. C star and C have the same size, but C star is the C center. So for every set of C centers like C, the cost from P to C star will be less than the cost to these C centers. So this inequality is by the property of C star. And now this is by the property of the cross set. So we already saw that the distance between every point of P to its closest point in C is epsilon compared to the cost of the query itself. So now, if you combine Q and C, what we get is the cost PQ less than epsilon cost PQ plus cost this time. Okay, just put this one inside this one. And finally, actually not so finally, from 4, what we get is 1 minus epsilon plus PQ is less than the cost of C star to Q. Okay, so we have some bound. It's based upon C star Q. Oh, the other side, right?
Better this down, yeah. One down, one's the middle.
And then the other one up?
Yeah. It's suboptimal.
Yeah, good approximation. Okay, so now without loss of generality, I want to assume that epsilon is less than half. Why can I assume it? Because if you have epsilon, if you have coset for epsilon, then you have coset for any value more than epsilon. This is by definition of the coset. So if we have coset, we give you error quarter, and you want it's also give you error less than half. So quarter coset is also half coset, and so on. So you can do the other direction, but you can always bound epsilon from above and assume that this is less than this value, and this will be good enough. Otherwise, we just assume that the epsilon is half. And from this assumption, 1 over 1 plus 2 epsilon equal. So I add to epsilon and remove to epsilon. That's all. We didn't do nothing. But now I can write it like 1 minus 2 epsilon divided by 1 plus 2 epsilon by taking these guys. And this is less than 1 minus 2 epsilon divided by 1 root half 1 minus epsilon 1 minus 1 plus or even 1, and this is less than 1 minus epsilon. Here we use the fact that epsilon is less than half. So we know that 1 over 1 plus epsilon is about 1 minus epsilon. It's also a popular equation in process construction, and now we can put it in our equation, so we know that cross PQ divided by 1 plus 2 epsilon is less than 6 1 minus epsilon cos PQ, which therefore is less than cos 6 q. And now if we take 1 and 7, we get that cos PQ is less than 1 plus 2 epsilon cos 6 q, and you also have the other direction by 1. So this is what we wanted to do. So again, I mainly use here triangle because there are not too many sophisticated theorems on data geometry, but it's still quite easy. And also the concept paper, actually there are very beautiful ideas and observation, but when you actually try to prove things, you get a lot of lists of these kind of equations. Again, not too complicated, but take a lot of space. But don't worry, when you have the intuition, like I try to give you in the picture, is not that bad. But it's good to go over it at least once to get familiar with this trick. The tricks usually repeat themselves in the equations. So in the context of talking about maximum distance, and we have, unfortunately, we don't have a general framework for maximum distance, but we have a nice general framework for process construction that I will talk about tomorrow when you want to do sum of distances for some object. And as a warm-up, I will talk about the problem of ring queries. In this case, the input is again endpoints in RD. Query is a point before, but now we want the sum of squared distances to this point. So now the K version of this problem would be the K-means, the famous K-mean problem. And we want to do similar trick as we do for the K-center to see how we can compress the points. So again, I give you all the points today. Tomorrow I'll give you one query point Q. And now we need to tell me what is the sum of squared distance to Q. Now this is an exercise that you should be able to solve. And quite straightforward. Any ideas? Is it okay?
Well, before you can slide them both down into the third one. It doesn't really matter.
There's another one, right?
At this point, they can't see that many stuff.
Yeah, let's connect back to this one. So you should be able to solve this one. So actually, the process is just of 1 point, not 1 over epsilon, not epsilon to the d. For any d, for every epsilon, you get the coefficient. And actually, the coefficient is equal to 0. I mean, epsilon equals 0. So we get the exact result using just almost 1 point. Any ideas? I see some hands. More? Guesses? Someone has a guess what probably would be the good solution? So what is the point of minimizing some square distances? You know, this is one of these. What is the point? Give you a set of endpoints. You know, a line, okay? The points of a line. The one center is the point in the middle. What is the one mean? What is the point to minimize some square distances to the input points? The mean, right? So if you have a street and you have a lot of customers and you want to be close to all the customers, the point to minimize some square distances is the mean. By the way, anyone know what is the point to minimize the sum of distances without the square? Median. Good. You know how to prove it or just guess? Okay, the proof is a bit more tricky. But let's stick for a moment with the one mean. So what is the core set? This is some people. Yeah. So actually, again, the core set is strongly related to the optimal solution. It was the case for the case center. The same case here. There's a strong relation between the optimal solution and the core set. And since we don't want to know the optimal solution, sometimes we just use approximations. But in this case, it's really easy to compute the optimal solution, which is just the mean. But how can we use the mean to answer these queries? Yes?
To the component-wise mean.
Excuse me?
Component-wise mean.
What is component-wise?
We would just take the first component of the vectors, they calculate the mean, take the second one, calculate the mean.
Yeah, good answer, but they're much more complicated than we need. I think it's correct in general, but there's really, really straightforward solution. So let's just try to write down what we're trying to do here. So we want to compute this time, right? Sum of square distances of all the points, right? But let's use algebra. I think we learned algebra so many years. Sum. What is this distance? This is just a norm. P minus Q squared, right? Completely unknown. The distance between 2 points is completely unknown. But now, you can open this. So, 1p squared plus right? Just open it, just simply touch it right. Now, I have this. I just open this one. It has 3 terms. First one is this. The second one is this. And the last one is this. Okay, how can we compute this in all one time? So this is just a number independent of Q, so you compute it tonight before you see the query. It's just a number. You compute it once, all n time or n time, and you have this number. For every query, you have this value. What about this? This is just n multiplied by norm Q squared. So when I give a Q, just compute the norm of Q multiplied by n, and you get this term of one time actually, or of d in general. How can we compute this? Actually, here we have a sum of n terms which depend both on P and Q. So how can we get rid of this? So again, using algebra. This we can just put the Q out. Q is not part of the sum. This is just also the 2. So when you're doing a product, you can take the Q outside, it's not part of the sum. Or if you want, you put parentheses here. So, and this is actually the sum of the points, which is the mean multiplied by n. So all we need is to save this vector and the number n. In the variance, that's it. So all one time for every query, you can compute this cost. But again, this is a very, very different cost. You need the subset of the input, and but you still can compute the cosine of 1 time. So for this, we just do all the equations that I wrote on the board, but now when I give you a query, you need to compute this strange function, but again, you have 0 error. And again, it's very different courses than the other courses that we saw. So we have courses that is subset of the input. We have the courses where we project the points on the line, so it wasn't a subset of the input, but it was still a small courses. Now we have courses of 1 point with additive constant term you must add to get the right value. So you see very different kind of courses. And in the beginning, we also saw courses when we have actually more points than the original, but we have good representation of the endpoints on the line, so we can store all the points efficiently. So again, this kind of different courses that we have. But again, we tried this in the recent year to have more general framework or general properties of a problem. And we'll see some of these examples. There are some open problems they want to mention in this concept. So we don't understand why heuristics work better on the cost compared to the original data. We already mentioned this problem, and it's still a mystery to me. When I show you this tree, the order of the points is not important. For a lot of paper or online algorithm, they say we assume that the points are in uniform order or something like this. When I computed this streaming tree, there was no assumption there about the order that you give me the input. But in practice, we see that this is important. For example, if you have all the points here and half the points here or half the point here, it matters what order they give me. If you give me this set and then this set, for 1 point from here and 1 point from here. So, can we say something about what is the optimal order in the stream, and can we do something smarter than just take the stream of points in arbitrary order? This is, I think, another very practical problem. Parameter calibration is another issue. So, for example, my students observed that if you, for example, can change the epsilon over time, you can actually bet much more sets. And it's not clear in the tree, so in theory, we just compute epsilon cost over time. But sometimes, especially if the cost is very small, you can compute actually epsilon cost with very much larger value of epsilon. So a good idea might to change the value of epsilon during the tree and again get much better cost, but we still don't have clarity of this. Again, because most of the results of the theory people, they try to have very general and natural results, but in practice, it seems that you can do much better. If we talk about problem like k-mean, the usual problem of how to calibrate not only epsilon but k, usually we just use some really parameter estimation, but also in this summer school we saw some ideas how maybe we can calibrate the parameters a bit better. There's also the sketch technique. This kind of competitor to the course. So in courses I talk mainly about subset of the input or very small set of points. Maybe I once before write the definition of the course. So if you have sketch in some sense. So if you have a matrix A n by d, and you have some random matrix, say log n by n, this is the coset in some sense. Then you get a matrix C side only log n by n. So usually S is a matrix that you construct actually before you see any entry of A. This is also very different from coset. In cosets, you compute the coset based on the input. In sketch matrix, you just take a random matrix and some distribution with some Gaussian entries, independent of A, and then we start to get points of A and update this value. In turn, because this is just multiplication of matrix, it's very easy when I update A, when A goes to A, you just change entries in A. It's very easy if you have S to update this term. In particular, this technique also will help us to change only coordinate of A and delete points by just changing the coordinate to 0, which we can do in cosets. But this technique also only works for matrices. It's hard to see how we can do this for triangles or chairs. unlike the very combinatorial framework that I defined the courses in the previous slides. There is some belief, some people believe there is, if you have courses for a problem, you can probably have a sketch for a problem. This means small metrics to compress the data. And so far, it seems true for most of the problem courses we have sketch. Most of the problems we have sketch matrices, we also have courses. And it seems that I believe, and other people believe, that this is some dual space and we can prove some connection between these two communities. I mean, in some sense, every row of this matrix is just a linear combination of rows in this matrix. So this is kind of generalization of the mean problem that we solve, that we sum all the points and take the mean. This is a lot of linear combination of the input points, so we take a lot of means, a lot of subsets, and this is the corsets. Unlike the course approach, when you take subset in a combinatorial way, for example, non-uniform sample, random sample, based on the input. Another problem is here we talk about let P be a set of points in one course for every possible P. And I show, for example, counterexample when all the points are on the line. But in practice, we usually have a lot of structures in the data, and we don't want courses for every set under the sun. We just want courses for our type of problem. So, for example, if you know that there is a good clustering in the data, or we have some distribution that the data come from, then maybe we can have much better courses, much smaller courses. For courses for problem that we in general don't have courses. So this is another great research direction if you're looking for a problem for your master or PhD studies. So can you have courses if you have assumption on the input, especially for important problem where we don't have courses in general. So if you assume something about the input, can you have better courses? It's quite amazing that, again, a lot of people talk about dealing with outliers, how many outliers we have in practice, but there's very little problem with provable guarantees and solution of provable guarantee of dealing with outliers. For example, consider this problem. You have, so we agree that the point at minimum sum square distance is the mean, right? So suppose they give you n points. And you want to find the point minimum sum square distance to the original point, but if you ignore the two farthest points, the 5 farthest points, can you solve the problem now? So of course you can, if I tell you what are the 5 farthest points from the center, you can just compute the mean of the rest. And actually, n choose 5, which is about n to the 5 possible couple of 5 outliers, and you can check all of them. It would be a bit too much. So the question, can you do this visually? Even for this problem, one mean point on the plane was open and still, I think, 2 years ago, the paper with Lorna Chuna, we solved this kind of problem also for line. But for example, for subspace, this is still an open problem. To put a vector machine, for most of the famous machine learning problems, we still don't know how to solve the problem with outliers. And there's a good reason. This is a very non-convex problem. But if we just want to do courses, and maybe we run heuristic or result research on the courses, it seems that this should be possible based on, again, existing results. So this is another great direction. The last thing that maybe is going to try to change these days is, again, a unified software library that you can run. Hopefully also we hope to do this in Galileo and Raspberry Pi for the Internet of Things. Use all these clouds and algorithms in practice and code them. Please keep visiting my website, and I hope very soon to publish a library that you can actually check this kind of courses on new code, maybe even for different problems. More questions now? More questions? Okay. So let's define the k-median problem. So in the k-median queries, it's essentially the same problem. Now we have 2 queries, 2-point queries. And in the k-mean, we want to compute sum of square distances. In the k-median problem, we want to compute sum of distances. So now we have 2 problems. You cannot do the trick that we did here, because first of all, it's not sum of square, it's sum of absolute distances. So you cannot just open this like we did here, the squared norm. You don't know how to open the non-squared norm. And you also have this mean here. So even if it was square distances, the mean killed all this approach. So can you have courses for the k-median problem, k-mean problem? And for this kind of problems, we show a very general framework that is mainly based on the basic dimension and another time called sensitivity. And we show how to solve this problem. In general, the motivation, of course, for example, we show also that this slide, I think it was a private course of papers, that we want to know how to put the facilities, and we want that the facility will be close to all the clients, and now we're interested in this minimize the sum of square distances. And again, we want to test several candidates. So for example, the motivation is for the k equal 1 case. So we know that the point that, let's return back even to the k equal 1 case, we have a set of points. And we agree that the point minimize sum of square distances is the mean. But what if I want the point that minimize sum of square distances, but it shouldn't be inside Boston? I have some hospital here, some farm here, so you can't put your store in this area. So now we want the point minimize sum of square distances, but you have a constraint. So the surprise is that we can still use the corsets, because the corset guarantee that for every q, the cost of the point to the query is approximate by the cost of the query. So not only the optimal solution is preserved, so not only by this property we have that the optimal solution for the corset of the query is less than 1 plus epsilon, the minimum solution for the original data. But you also have the query that if you have the property that if you're allowed to use only a subset of the queries, we want the optimal query from a subset, for example, because we have restricted zones, then just change Q to Q prime, and this still holds. If you have optimization problem under strange constraint, like the optimal solution, the solution must pass through specific lines and be very far from a specific area, we can still use the same cost approach. Of course, we need some algorithm to solve this optimization problem, but then again, the set is so small, so maybe we just use exhaustive search and run the heuristics in enough time. So, how can you compute in general a k-epsilon median corset? So, again, the idea, as I saw in the clustering case, just compute a representative for each set of points in space. So for every cluster, take a point. The main disadvantage, this technique, as someone already pointed out, it's exponential in the dimension. When you go more and more dimension, we have exponential number of cells. So after the first paper appeared, we kind of, I think the first paper was by Chen, showed how to compute corsets for k-median and k-mean on high-dimensional space. And instead of using this clustering grid, we just find a distribution over the space and sample point according to this distribution. So, try to give you some hints how it works. So in general, we still have ways for each cluster, but the cluster won't be grids as we had before. And in this case, we say that C is a k-epsilon corset for P for every set of k stars, k points. the sum of distance from the point of P to Q is 1 plus epsilon approximated by the sum of weighted distances. So again, you're bringing case files, you want the sum of distances. You can approximate this just by taking the weighted sum of distances from the red points. And in general, what we'll see tomorrow is that we can have causes for any kind of problem if you want to minimize sum of distances. The distance can be a very general function. So in general, as before, we assume that P and Q are two sets. We have a distance function now for every point in a query, not all the set, just a point. And then what we want is to approximate this sum, the distance to a query. So then all we need is to sample point, but in non-uniform version, non-uniform way, according to this distribution. So this is the probability to choose a specific point from the process. The probability says essentially how important is this point compared to the other point. So for example, when you have minus a point here and 1 point here, why this point is important in some sense to the concept? It is important because if we give you the query here, this point dominates the cost. If you won't take this point, all these are 0 essentially. If you won't take this point to the concept, you won't have good approximation. On the other side, all these points for the query are actually have neglected cost, so you can ignore them. So based on this intuition, the definition of sensitivity is, for a specific point P, is take the worst case query. Take the query where this point contributes or dominates the cost. So compared to all the general cost for all the points, the contribution of this point is maximized. This defines how important this point. And we hope, of course, this number is less than 1. We have value in the sum of values. But we hope that the sum of all the points is not n. It's only like log n, because this determines the sum of the cost. And intuitively, if all the points are important, we need a cost of size n. But we hope that in general to prove that no matter what set you give me, very few set of points are important. And in general, we prove that we can have cost sets where the size of the cost set is the sum of the sensitivities. All the points multiply by 1 over epsilon squared. This is where you pay for the error. Here, there's no epsilon. Only now you put the epsilon. And we need another number, not just the sum of sensitivity. We also want to know that the queries are not too complicated. And for this, we use the visit dimension of the query set. So we don't have too much time to talk about it, but tomorrow we try to prove this theorem and have some more intuition. How can you compute process for problem like k-mean, k-median, and other version using just non-uniform random sampling, both this is based on this sensitivity. And we also answer the question how we can actually compute this sensitivity, which sometimes can be a very hard problem to solve for each point. And I see that we're running out of time, so it's a good point to stop. Any questions are welcome, and I'll also be here the next hours. More questions? Okay, so thank you very much for your patience.
No, we don't have break.
And the process. We'll tell you when I find things. In the break room. I don't know. I've seen one and I wonder who it belongs to. Outside people. Okay. Let's give it a second for everyone to settle down, and then we have to continue. I'm not sure whether those desks where there are laptops lying around, those people will probably come back. Right? So we have a couple of free laptops. What do we have? MacBook, something that looks like a ThinkPad. Yeah, it's good. Good deals.
Shall I wait for you to go? Oh, no,
Give people a chance to come back. Oh, what's this? Okay, welcome back to the third installment of the path towards resource-aware distributed machine learning. The last 2 days, I talked about, the day one was purely slideware on, hey, resource management is upon us, we need to do something in this space. And we can do something in this space because of machine learning. We do have some flexibility in how we execute our algorithms. For once, we often don't care about the order in which we visit the examples. And in other cases, we might actually do away with some of the examples without doing much harm, so we can run on samples. On day 2, yesterday, I presented kind of the minimal distributed program that you can write in Reef called Hello Reef. Some of you successfully installed the dependencies through the narrow Wi-Fi, and we talked about running it on several runtimes, and we only did it on the localized. This was the slide of doom yesterday, where all of a sudden everyone was kind of on the Wi-Fi and we had a little bit of congestion. So who was able to install all this software since then? Awesome. So today we can assume that most everyone has it. For those of you who don't, I published these slides of yesterday onto the reef-project.org website, so you can follow the links up on there. And given that it's about 5 people right now who didn't raise their hand, it should go smoothly in parallel to the lecture. So I want to quickly go over what we did yesterday because it was a little bit confusing because people were on different timelines. So we compiled Reef, which depends on Wake, which is our messaging library, and Tang, which we use for configuration also in Wake. So whenever you do any sort of compiling it anywhere, you want to compile Tang before Wake, before Reef. And when you compile Tang, we fetch it from GitHub. All of our code is hosted on GitHub. And then you just compile it with the standard Maven commands. So MVN is the Maven command. Oops, I'm only on this screen today. And then skip test is just skipping the tests. Clean install means compile it and put it into the local repository. And then after some time, you get a build success message. Similarly, when you compile Wake, and also, I assume that everyone who raised their hand earlier also did this since yesterday, right? Did this all? Who has not installed Tang, Wake, and Reef? That's all right. I'm willing to just move ahead with 3 hands up. So what you want to do is you fetch Wake from GitHub again, then compile it, and it will install itself into the local repository. Life is good. Last step was to compile Reef. In that case, you fetch it, you check out the MLSS branch. That is very important for this lecture, because we will use functionality that's not currently in Reef master. And then you compile it, and you see the same sort of printer. Now, for those of you who did this yesterday, can I please ask you to do a git pull in that folder and do the mvn clean install again? Because yesterday night, and while you were listening to talks today, there were some changes in the software that will make the work today and tomorrow a little bit more smooth. So you want to pull the latest version of the software. That's what git pull does. It fetches the latest version of the repository from GitHub, and then just do the mvn clean install again. Questions? Yes? You just go into the Reef folder, and then you punch in git space pull.
In the master branch or MLS?
In the MLSS branch. You should already have checked that out, right? Okay. So, what we also all did yesterday, or some of you did yesterday during the lecture, and some of you did later yesterday or today, is to run it, right? So, again, a quick reminder, we have 3 runtimes in Reef. The local runtime to execute things on your local machine, where each of the processes that you have in Reef is run as a local process, as opposed to a remote process. Yarn, which is great when you already have a Hadoop cluster. HD Insight is great when you would rather rent one and have someone else worry about the installation. In this tutorial, we will not use the Yarn runtime. Okay. So just a quick check. Who has been with me on running Reef locally? Who has done this? Okay, this is slightly thinner than earlier. So what you do when you run Reef, and for those of you who are not Java programmers, I want to explain it. For those of you who are Java programmers, go and read your emails for a minute. So what's happening here is you call Java, -cp stands for class path. That's basically the path at which Java will look for all the classes that you want to load. Where's the binary code, right? That's what this -cp does. And then in the Reef examples, there's a subfolder target that has been created by Maven. Whenever you compile anything with Maven, the outcome of the compilation will always be in the target folder. And then inside of that, there's this enormously longly named file which ends in .jar. That contains all the code that we compiled, right? And it's enormously long named because, well, the first 2 is just the name of the project. Then there's a version string, which happens to be 0.6 snapshot. Snapshot means it's not released yet. And then at the end, it says shaded.jar. That's because we munched together a whole set of libraries into one convenient package for you. And after that, you specify the main class that you want to run. Right? That's how this enormously long command line comes together. And the class that we want to run is called Hello Reef, and it's in the package com Microsoft Reef examples hello. Right? Yay to software design with namespaces and all that. That's why it comes out to be this long. Okay. I had a couple of hands up who have done this. Have any more achieved doing this while I was explaining it? Okay. Yes, do you have a question or you? Yes.
What's the branch name again?
The branch is MLSS, all caps. So if you have questions like that, please always ask, right? Because you can be lost on a very small detail, and that would be unfortunate. Okay, when you run this, you will see some printout like this, and at some point, depending on how many logs you print out on your machine, you will see this, hey, there's a job completed. In this case, the Hello Reef job is completed. And some of you actually asked me yesterday, hey, where's the Hello Reef? So the Hello Reef ends up, remember, this is running on a quote-unquote remote machine. In this case, that remote machine happens to be a process on your computer, so it's not that remote. And we store all the output of those processes in a folder. So when you look into where you executed the prior command, you will see that there's now a folder called Reef Local Runtime. That is just a constant name that we use for all the output of anything that has been run on the local runtime. So when you, for example, where you, for example, to compile Reef with tests, you will see dozens and dozens of jobs that have their subfolders in there because we run Reef jobs as part of the tests. Now inside of that, you have a folder that's named after the job that you ran. In this case, Hello Reef dash some number, and that's the timestamp of when you submitted the job. And inside of that, you have a couple of folders that all start with note dash a number, and that's just the number of virtual machines that you run. Dash, again a number when they were launched, timestamp, and inside of that you have a file standardout.txt. That's where everything that this process printed to standard out in Java via system out print line ended up. We capture that in that file. So and if you cat that, you will actually see that Hello Reef was printed on the screen of that non-existing remote machine. Who has seen that? Okay, we're doing much better today than yesterday. This is awesome. Okay, and I went over all of this. And again, those slides are on the Reef website if you want to follow up. So now for new things. New things are, let's run things on the HD Insight cluster that we provisioned. In this case, it will actually run on a remote machine. HD Insight is a fully managed Hadoop in the cloud. You walk up to azure.com, which is the Microsoft Cloud website. You log in, you give us your credit card data, you click on the button, hey, I want an HD Insight cluster, and you can make one for yourself. We skipped the setting up and paying for it for this summer school because we paid for it. But this is the general approach on how you would get an HD Insight cluster. You just go to the website, ask for one. You don't have to download software, install it on 100 machines or so. So all of this is managed for you. When you submit a job to HD Insight, this has two steps. They are both done by the code that we're about to run, but it's important to understand that both of these happen. The first step is that we upload what we call the job jar to storage, to Azure storage in the cloud. That is, the code that you want to run is uploaded to some storage device in the cloud from where it can be accessed from where it can be accessed by the cluster itself. So this is, you will see this when you run it. This is the majority time that you will spend waiting for your job to run. It will say starting to copy file to Azure storage, and it will take a while because we are a little bit rate limited in this room. And then you can submit a job which actually tells HD Insight, hey, go fetch that file from Azure storage and run it. All right? Okay. So now this is the business where we need the JSON file that I was handing out on a USB drive yesterday. Who has that file? Okay, who does not have the file? That's equal amounts. Can I get one of the volunteers to quickly switch off the camera because I want to show the location of the file?
The streaming one?
Yes.
Okay. Is there something you don't want even on the recording either?
Yeah.
Can you like, let's just like put the cover over it or something like that. Actually, just put your hand over for a second. Here, I will just do this for a minute. Oh, no, that isn't. Wait, where's the? Oh, the camera's up there.
Okay.
Here's what we'll do. So you stop the video? Oh, don't. Okay, don't stop it. Just put the cover on.
Okay, so we are offline?
Don't, not quite yet.
Not quite yet, okay.
Okay, just, yep.
Wonderful.
Yep. Okay.
So this is the link under which you will find, when you browse to there, you will get a kind of Word online which has the content of the file. Just copy that out of this into a text file and save it under a name that you can remember. The reason I don't want this on the internet is because it's quite literally the keys to the 1,000-core cluster. And someone will find nefarious purposes for uses for this. I'm sure no one in this room will, but things get recorded and weird.
You can almost see it in the reflection up there, but you actually can't. I just realized that. It's not legible, fortunately.
Oh, right.
Yeah.
Point the camera towards the audience. So if someone on the video stream can't figure out that URL, then I'm fine with using the cluster. Because it is fairly blurred. So have you all gotten the file? Who's still working on that? Who has given up? Okay, so you all have it? Can we kind of have the internet audience join us again? No one complains, then I'll move on. Okay. I'll go to the next slide. Woohoo. Yes, now I'm in the picture again. Okay, so now that we all have these credentials, what you will have to do is you will have to set the environment variable called brief_HDI_conf to that file, right? It needs to point to that file. So if it's in c:\mlss.json, then set c:\mlss.json as the path. If you are not in PowerShell, then you will do $reef_HDI_conf equals that string, right? Not do the $env copy. You look confused?
You're exporting the reef variable or the environment?
So I'm setting a reef_HDI_conf to be this value. So in Bash, what you do is export export reef_HDI_conf equals that value.
Sorry, what do we do in Bash?
So let me type it and try whether I get it right. There you go. So what you do in Bash is probably, and the people with Macs in the room correct me, you say export, okay, without the capital E, reef_HDI_conf equals to MLSS.json.
That definitely has the key that I can see on the right there. On the left.
That is not good. There we go. Now it's out. Well, we'll just use a new cluster tomorrow. This one might be hosed. Okay, I suppose that this line works for people on Linux and Macs. If it doesn't, then I have forgotten more about Bash programming than I care to admit. Okay, we will all know whether it worked for you with the next line, and that is again one of these really lovely long Java invocation lines. So inside of the reef folder, you will find that there is a folder called reef examples HD inside. And inside of that, there is a target folder, and inside of that is this file, the reef examples HD inside snapshot shaded.java. And then you run the com Microsoft reef examples hello HD inside class. I can do this in a terminal such that you can kind of follow along if that helps more. Let me do that. You don't see me? Let's see. So if you look into the reef folder, there is this subfolder called reef examples HD inside. Oh, the highlight didn't come through. What you need to do is java-cp, again for class path. Oh, let me do this. Java-cp, reef-examples-hd inside, target, reef-example-hd inside, snapshot-shaded.jar. That's the joy of Java development. Everything has very long names. And then the class name is called Microsoft Reef.hello, examples.hello.hello HD inside. Okay? Unfortunately, as soon as I hit enter, there will be lots of log output and it will scroll past. So I don't quite know whether I made it happen myself. I'll keep it up for a minute or two longer. And don't worry, we will go over the actual code that you're invoking here later today. Okay, I will run this now, and things will scroll through my screen, so hopefully that won't confuse people. That's a lovely little warning message that I put in there. Don't get confused because of that. It's because the release of HD Insight we use hasn't been released, and the server we run on doesn't have a valid certificate. That's why I had to switch off the SSL certification. Okay, what you see here is, well, you have our usual banner, and then at some point it says uploading longpath.jar to kind of longpath.jar. This is the step that I mentioned where your job is uploaded to Azure Storage, and only after that can be submitted. And when you submit an application, you get an application ID back. That application ID can be used to later on fetch the logs of the application and to query its status while it's running. You look very unhappy. Can I help? No? All good? So for example, what we can do, and that's the thing that I was coding while Dan was giving his lecture, is we can do java-jar. This is again, unfortunately, a really long path. Oops. Oops, sorry, wrong path. Examples, HD inside, target, dash shaded.jar, dash status, and then give it this URL, this name for the application that you got, not the one that I got. I got 99. Someone must have 100, someone else must have 101, and so on. And when you run this, it might take a little while, depending on how our network connection is. You will get a printout that looks a lot like this. This is just the status of the application. In this case, it has a progress of 100%, which means it's done. It was running on some queue. Queues are the various means by which you can execute things. The very important statement that you want to look for is this final status. What this suggests is whether or not the application was actually successfully executed. For Hello HD Inside, it should almost always execute successfully, right? Because it's such a simple application. If you have an application that has a bug or anything, you will not see the succeeded, right? While it is running, and we will see this with the machine learning examples tomorrow, while it is running, it will actually say running because, well, it's not done yet. Before it is running, it says accepted, which means your application submission is accepted by the cluster for execution at some point in the future when containers become available. Right? So that final status here is the interesting bit to figure out what happened to your application. Yes?
Can we use the other projector?
Can we use the other projector? I don't know.
Yes,
I suppose that would help you guys on that side of the room, right? a lot.
We should replace this as ERV.
Yeah.
Okay, you know how to operate that.
Can you show the history?
I can show my command line, yes. So, who has successfully submitted Hello Reef and seen the status completed for their job ID? Who has successfully submitted Hello Reef? That's considerably more. Okay, so this is the command line that you have to run, and unfortunately it's a long one again, to get the status of your job. It's one of the fancy setups, so I can have the second to last slide on this one.
Oh no, it's just the
Okay.
same.
So
Yes.
it shows failed by the command
Yeah.
for some reason.
It shows failed? For whom does it show failed? For whom does it show succeeded? Okay, whom of those who say failed are on the CMU secure wireless?
No. Application.
Are you on the CMU guest wireless?
I am.
No?
Yeah.
Hmm?
No.
And it still fails? Okay, we'll have to look into that. That's wonky. It should have succeeded. We'll look into this. I'll be in the break room after this lecture for the hour between now and the dinner, and we can look into it, why it didn't work on various machines. It should have worked, but there are always things that we can't predict. Okay, so in that case, I will just show you what happens when you do -logs on the same command line. Oops. Oh, what was the ID? I need the application ID for this. There we go. So if you do logs, it will go ahead and fetch the logs of the application. And the second parameter on this call is a folder into which you want these downloaded. And just by convention, I always use the application ID. So if you go into that folder, you will find one file per container that you ran on. And if you look into this, actually the second one is the interesting one. You see that on the standard out of this evaluator, you got Hello Reef. So for those of you where it failed, please come see me after the lecture. There's something wonky going on. Okay. That's the peril of practical lectures, right? Okay. So, but you did get a printout, something like that, when you get the eventual state was failed. So you submitted the application, and then the eventual state was failed?
Yeah.
Yeah.
Okay, we'll look into that. Okay, I already spoke about accessing the logs. It will be on the slides that I'll put online after the lecture. So this is how you can check for the logs. You give it the ID of your application that was returned to you by the submission, and then a folder where you want to keep the logs when it downloads. So what this does is it goes to Azure Storage where all the logs are stored, fetches them and puts them into a local folder. Those logs are by definition only available after your job exits. So while your job is running, you unfortunately do not have access to the logs. So you always have to wait for it either to, not finish successfully or finish successfully. Okay. So for the last half hour of today, I will do slideware again on some of the concepts behind Reef and what kind of flashed through and all that. And after that, I'll be here for another hour and we can work through the practical kinks of why it didn't work for some people. So you've seen on many of the slides that I used yesterday and before that, the word configuration thrown around, and there was this code that was making configurations and all that, and I completely brushed over that. Today I want to give you more details on Tang. Remember on the first day I showed you kind of the feature presentation of Tang, that can turn nasty null pointer exceptions into something that you can actually parse, which says, hey, you missed the parameter. I want to tell you a little bit about the backgrounds because this will be very helpful when we look at actual code and how to write applications on top of it. And in good computer science tradition, we have a hello example. In this case, it's called hello tang. So hello tang consists of an interface called message printer, which has a single method, print a message or print message, right? And you can imagine what that message will be, right? Hello world or something like that. And then we have a class greeter, which needs a message printer as a constructor parameter, right? This is a very common design pattern. You can think of, if you want to think in machine learning terms, then this is your optimization algorithm, and it depends on a loss function implementation, right? You want to kind of make the objective function known to the optimizer. And then in the method greet of this greeter, printer's print message method, right? So far, so easy. Now, we also have an implementation of message printer, which happens to which is called hello printer, and in its print message, it just prints hello, right? So there are these red things in this code, these two add injects. They make these constructors known to Tang. So Tang will consider these in the following sense. When we make a configuration, we can say bind implementation message printer to hello printer. So whenever someone asks Tang to instantiate a message printer, Tang will go ahead and make a hello printer. When Tang is asked to make a hello printer, it will go ahead and consider only the constructors that are marked with add inject. So this add inject is an annotation in Java. And then, of course, sure enough, you can go ahead and use this configuration to form what we call an injector. That's make for objects. That's how you can think about it. And say, hey, give me an instance of greeter.class. Tang will go ahead and look up a constructor for greeter. There's only one. See that there's a message printer needed. Then we'll consider the configuration given and see that, hey, the hello printer is bound to this. And then look for a constructor here, and gladly this one has no further dependencies. It can just instantiate this, and it will give you a greeter instance which has hello printer as the constructor parameter. So for those of you who predominantly code MATLAB, this is all Spanish, right? I understand that. I will go over why this is cool and what it helps with. Sure enough, this prints hello. I have a visual representation of how we speak about these things in Reef. So we have the class greeter, which happens to depend on a message printer instance, right? And message printer happens to be bound to hello printer. The crucial bit is that these dependencies are in code. So the greeter class had in code declared that it depends on a message printer. Or your optimization algorithm states in code that it needs a loss function, right? Or your kernel machine states in code that it needs a kernel, right? And then these bindings, this is bound to statement is in the configuration. So someone who uses this greeter can tell it which message printer to use. Someone who uses your learning algorithm can tell it which kernel to use. And I have this in a couple more examples, because I understand that this is really kind of the hardest to grok part of Reef, right? That everything else is kind of straightforward processes on various machines. So okay, so we do hello tang in German. So instead of the hello printer, we now have the Guten Tag printer, which is just printing Guten Tag. It looks the same, everything else is the same. Someone else could have written this, right? This doesn't have to be even in the same code base. And then in the configuration, only one thing changes, right? Whenever someone asks for message printer, give them the Guten Tag printer. And of course, it prints Guten Tag, and life's good. So we had this picture, and we swap it out for this picture. Nothing in the code changed, right? Because I told you that these dependency statements are in the code, while the binding statements are in the configuration. Now this is all well and good, right? We bind various implementations to interfaces. Why bother, right? You can just as well have some statement somewhere which says, if command line parameter suggests logistic loss, just code up new logistic loss, right? This doesn't make many things much easier. Let's talk about some of the things where this makes life a lot easier. French is harder than German, especially for me as I'm German. So let's talk about hello tang in French. In this case, I kind of got tired of writing yet another implementation of this message printer, and instead I declare a parameter. And in Tang, we use /abuse the Java type system to identify parameters. So this name here, message parameter, is now used to identify a parameter. And I will show you how that's used. We make ourselves a configured message printer, which has a message inside and prints it out. And just like before, the greeter would depend on an instance of a specific interface. This constructor depends on a value for a specific parameter. So you can now set this value to be whatever you want, and this class will pick it up. And again, this is where it becomes interesting. If you think about someone plugging in a kernel into your kernel-based learning algorithm, and that kernel having parameters, how many if-then-elses you have to write to pass the command line, right? Because all of a sudden, if it is a Gaussian kernel, you want the radius. If it is the polynomial kernel, you want yet another parameter. In this world, very little changed, right? Because we can say, we want a configuration where whenever someone asks for message printer, we make the configured message printer. Now, in addition to that, we say, okay, when someone depends on this message parameter, which we call a named parameter, because it's a parameter that has a name, we give it the string bonjour. And then, from the perspective of the greeter class, nothing changed. It gets a message printer. How that thing was instantiated, whether it has parameters or not, is completely immaterial to this class. You can just write it as if you had an instance. And then, of course, it prints bonjour. So in pictures, this means we had this, right, for the German version. Now we go ahead and replace the Guten Tag printer with the configured message printer. That guy now depends on the message printer, the message parameter. And that is bound to a string. Now, again, all these dependencies are in your code, right? Your loss or your kernel depends on a parameter, would be the machine learning translation of it. And then the configuration that your user fills out says, okay, that parameter shall have value 5. But just because you have this, nothing else in your code has to change. It's very nice to make composable software. And what you've seen in the code is that there are basically 3 steps in Tang. And I'm going to talk a bit about why Tang is designed the way it is. The first step is a configuration builder. That's when you write up your configuration. That's just standard key-value stuff. You set keys to have a certain value. We make it so that the keys are Java classes. That way you can never mistype, because the IDE or the compiler will warn you when you use the wrong string. We also do this trick where we make all the values right once. Again, for those of you who have used Hadoop in the past, in Hadoop the configuration is a giant key-value store that anyone has write access at any time who happens to get a handle onto that object. So just because you set a value doesn't mean that it prevails until your application runs. Someone else can override it. This can never happen in Tang because when someone else tries to write into your configuration, an exception is thrown and it contains both places when this value was set. So out of a configuration builder, you make a configuration. Configuration is immutable. It is pure data. This means that we can transfer it across the network without any issues. And as you might have guessed, we do Tang in the context of Reef. So the driver configures an evaluator. So the driver process makes a configuration and funnels this across the network. This is in contrast to systems like Juice, which is also a dependency injection framework in Java, which allows you to say, when someone asks for an instance of, what was it, message printer, run this little code that returns them a message printer. As soon as you allow this, it doesn't work anymore reliably in a distributed system. Because this code would have to be run on a different machine. And then all hell breaks loose, right? There could be state on that machine that's different from the machine where you configure things. It's one of the biggest reasons why Hadoop configuration is such a pain to work with. And I'm not making this up, right? The people who have tried to use or have worked with Hadoop have realized this in their PhD thesis written on the subject of whether or not you can predict out of a Hadoop configuration whether this Hadoop job will run or not, right? It's not, this sounds all very pedestrian for a distributed system or machine learning summer school, but configuring your software is incredibly complex and it's incredibly easy to mess up and write papers with non-reproducible results. The last step in this is we use the configuration to make an injector, and the injector is the access mechanism, right? You go to an injector and you say, make me an instance of a certain class. And it will consult both the code, which encodes the dependencies, and the configuration, which encodes the bindings, to create your instance. So for those of you who have used Hadoop, I have a couple of kind of comparison statements to make. Hadoop configuration is incredibly easy compared with Tang, right? There is no like 20-minute segment in a summer school necessary to grok what it does, because it's just a key value store. The keys are strings, the values are strings, life is good. And of course, it's super ubiquitous in the Hadoop space. The tricky bit happens because there's no type checks whatsoever. So if Hadoop expects a floating point number and you put a string there, when will you get the exception, right? When will your code not run? Well, at the time when it tries to interpret that value, which might be hours from the time when you actually submit the job, right? So I don't know how many machine decades I've wasted at Yahoo waiting for that error message, right? Just because there was a typo in the configuration, someone else overrode it, something like that. It's incredibly annoying and very costly, right? If you think about all those machine hours that are wasted. As I mentioned already, in Hadoop, it's very straightforward for anyone who gets a handle on your configuration to override parameters. So you set the memory that you want to have for your application to be 5 gigabytes, but some process in job submission overrides that with 3 gigabytes. You try to load your file into main memory, and then you get an out-of-memory exception. The configuration is not the first place where you start looking for the error, right? You will start looking for, ooh, is my file too big? Do I need to, chop it out a little different, stuff like that. But in reality, it was a configuration. And of course, typos are not detected early. Tang, on the other hand, has a fairly strong theoretical foundation, which allows us to be very, very aggressive in type checking and detecting typos early. We do have a static analysis tool that can tell you before you even run your application whether required parameters are set or not, and whether they are within the given range, and all of that. Right? So you can prove that your code won't run during compilation. If that comes back as it might run, then we can still try to detect errors as early as possible. Additionally, we made it cross-language. So we have a C# implementation and a Java implementation. But right now, that comes at a little bit of a cost. As you can imagine, for a project that's about 18 months old, it's somewhat immature. So some of the error messages are not as clear as we could make them, given what we have as input data. And for those of you who will write some software in Reef, you will hit that. And in those cases, please post a message on the mailing list of the form, I got the following convoluted mess where I instead expected this nice little statement. That will make our life much easier with improving the error messages. Composing configurations can be very awkward. Because of our write-once semantics, if you have two configurations, let's say someone gives you a configuration for how to load the data, and someone gives you a configuration for the learning algorithm. If they happen to use the same parameter, then you will get an exception because you cannot override them. So this is awkward. Right now, it's only used by Reef, so it's not as ubiquitous as Hadoop configuration. Of course, this again might change over time. Has any one of you ever worked with Juice? Okay, 1, 2. So if you compare Tang with Juice, Juice is a dependency injection framework that we initially used in Reef. It was open sourced by Google I guess, 2008, 2009 timeframe. The main differences between Tang and JUice, they share a lot of the general philosophy of making objects through code and all that. In Tang, configuration is pure data. The concept in JUice would be modules, and modules in JUice can contain code. That is this case of, hey, when anyone asks for an object of type message printer, run this code, it will return an instance of it. As soon as you allow that, this whole remote process configuration gets really wonky. Because that code could use local state that's local to this computer. Let's say it looks up the class name in a file, and that class name is not in that file on the other computer where you want to run it. And then you are again in this mess of having to run it to see the exceptions. That was the main reason why we decided to go ahead and build yet another dependency injection framework. The second reason is Tang generalizes across languages. So what we do is we extract all this dependency tree that is encoded in code into data, and we do this right now for Java and C#. There's no reason why it wouldn't work for C++ or Python or maybe Ruby. We just haven't done that yet. This allows us to do things like you have a Java job driver that configures tasks written in C# and vice versa, and we can check the errors early. Okay, so how do we use Tang and Reef? The first thing how we use it is we provision all of the Reef APIs through Tang. So if you want to have access to any of the APIs in Reef, the way you do this is you write a constructor and you depend on an instance of it. You just have a constructor parameter with an instance. This means that for all the APIs that you don't use, you don't even see them. That makes code a little cleaner, especially at the beginning when you don't interact with too many of the Reef APIs. The second part where we use Reef and where you will use it in code is to configure Reef itself. Applications bind their own implementations for all the event handlers that I was mentioning earlier, right? So when start time happens, that event is fired to an event handler that's registered in Tang. When you submit a task, what you actually submit is a configuration that contains a binding between the task interface and your task implementation. So we use Tang both to expose Reef APIs to applications and to expose application implementations to Reef. This interdependence makes very interesting things possible where Reef becomes very extensible, fairly straightforwardly. Lastly, we use it for contexts. That's another of those words that appeared on the slides. I never quite explained it well enough, and I want to do this for the last 10 minutes of today. And we had this example code for Hello Reef. By now, these configuration statements make some sense, right? Because we created a task configuration here with a builder, and at the end we say build, and we bind the task interface to an implementation, and then we submit a context and a task. So the task part of that should be fairly clear by now. What we do is we tell Reef, hey, when anyone asks for a task instance, give them hello task. If anyone asks for the name of the task, what we call the identifier, tell them hello Reef task. Right? So this is just a configuration that configures Reef to run a specific task. But there's this other thing called a context, which is also submitted as a configuration. And I want to talk a bit about that. So contexts in Reef are a way for an evaluator to hang on to state in between tasks. Think about you run a straightforward implementation of gradient descent. You submit a task that computes gradients, that sends a model back, gradients back. Some master computes a new model, and then you want to submit yet another task to compute the next gradient. It would be very convenient if you in between could hang on to the training data, such that you don't have to load it from disk again and again, right? That was the 30x speed up that everyone who improves upon Hadoop claims, not loading things from disk. So that's one aspect of of context. The other aspect is contexts can be stacked. So you can have more than one on top of each other. And the semantics are that the topmost context has access to everything underneath. Or in the case of a task, which is always the topmost thing running on this stack, a task has access to all of this. So think about the following. You have a context that contains some training data. And unfortunately, I'm not sure whether you can read this. This text is a context that contains training data that's sitting on this evaluator. But it doesn't contain the training data yet. It's just a placeholder. Now we submit a task to this that shall load some data. And while it is running, it is filling up the context with actual training data. Now when that task is done, the context sticks around. And all the kind of in-memory variables or files on disk or whatever this prior task created, they are still there. Which means that if you now go ahead and submit another context that happens to contain a model, and then submit a task to it, which shall compute a gradient, that task has access to everything underneath it. So it has access to the training data and to the model. So I was talking about that Tang is used for context. And some of you might guess how we do that. I have to tell you a few things in Tang that are just true that make it so much easier. Objects in Tang are always singletons. So if, for example, multiple places in your code depend on the kernel, they all get the same instance. Right? That's one truism. That's true as long as all of these objects are instantiated on the same injector. Right? When I go to an injector and I ask for an instance of your learning system, and inside of it there are dependencies which ask multiple times for the same instance, let's say the kernel, they will all reference the same object in memory. We will not instantiate objects twice. Now, injectors can be forked, which means that you take an injector and all the objects that have been instantiated right now, create a copy of it with additional configuration. So when someone asks for an instance of an object that was already created at the time this thing is forked, they will get the same thing. They will get the same object as before the fork. If someone asks for an object that wasn't part of this, a new one will be made. Now with both of these things being there, we can say that contexts are injectors. So if you think about what I said about when you write your code and you have dependencies on your constructor, those are met by some injector. And if that injector happens to be the context, then you can think about the code saying, hey, here's a compute gradient task. It depends on training data and model. And both of these dependencies are met by the context that it runs on. Right? This particular nuance is not incredibly important to know. What you need to understand when you write Reef applications is you can depend on things that are in the context, not by doing a get or any kind of key value store operation, but by just depending on instances of these objects in your constructors. And we will go over this in gory detail tomorrow when we actually implement a batch gradient. Okay. At this time we have 6 minutes left, and I want to do what I did at the end of yesterday's lecture and walk you through the code, but now with the knowledge about what's going on in terms of Tang and context. So, let me just, you don't see that either, right? Not that I'm giving away secrets again. Okay. There's some way to make this more visible. This is big enough, I hope, for the last row to see. Okay, wonderful. So this is the class Hello Reef No Client, for those of you who have installed an IDE and want to look at it. So we have this main function here, and this is just like in any programming language. In Java, there is a main which is executed when you run this class. It fills out a configuration, in this case, the local runtime configuration. And again, the runtimes in Reef, local or HDInside or Yarn, they just bind interfaces to implementations. Reef depends on certain things, like run something remotely. And the runtime provides an implementation of that interface. So in this case, we want to use the local runtime the local runtime has a parameter which tells us how many threads or processes do we want to run at most at any given moment in time. In this case, 2 is enough. 1 for the driver, 1 for the one evaluator. And then we call this run hello reef without client. I'll go over why it's called without client tomorrow. What we do here is we fill out a driver configuration. There's a little bit of boilerplate here, but what you see is we give the driver a name. Right? That's the string that you saw in the folder name, for example, when you run this on the local runtime. That's the name of your job. It also shows up when you do the status operation. It shows up in the logs. That's what uniquely identifies your job. For some of the code we'll use tomorrow, we conveniently put your username there, the username on your local machine, because if we all submit a job to the cluster with the same ID, it will be very awkward for us to figure out who submitted which one. Right? So this is the way how you make things identifiable. And then we bind 2 things. We say, when driver started happens, we want to have this class receive the message. Right? This is a tag binding of the interface or name parameter in this case. Driver started, that's the destination for the start event. We want an instance of hello_driver.startHandler to receive that. When evaluators get allocated, we want an instance of hello_driver.evaluator_allocated_handler to receive that. And again, this is Java, and names tend to be long. Okay, so now let's look at this hello driver. Oh, sorry, I didn't tell you yet that we make ourselves a reef instance before this. And a reef instance is this class that you can submit jobs to. And we make it by making an injector of the runtime configuration and then calling for an instance of, it's actually a bug or slightly not nice code, and asking for an implementation of reef. Right? So this runtime configuration could contain a binding that says, hey, when someone asks for a reef, give them the reef local implementation. Right? This way, we can make this code very generic, and the only thing that the user of this hello reef needs to change when they want to submit to, let's say, HD Insight, is provide another runtime configuration. Okay, and then on this reef object, there's basically only one method, which is submit, to submit a job to the cluster. And the submit method accepts a driver configuration. And the driver configuration tells us everything we need to know about what to do when things happen. And if you look onto all of the events that driver configuration has, there's any number of events that you can listen to. You can listen to on driver stop, on task completed, on task running, on evaluator allocated we already listened to, driver started we listened to, and so on. Right? And you can see at the type back there, that's a nuance of tag that I didn't go into, what is optional and what is required. Right? So you need to give us a driver started handler. You need to give us an identifier. You don't need to give us a handler for the stop event. Right? That's the default behavior that I was having on the slides yesterday. Okay. The actual driver. So the driver code is fairly straightforward. So I mentioned when we were going over the slides that the way you get access to reef features is to depend on them in your constructor. In this case, the constructor depends on one thing, and that's an evaluator requester. That's the class through which you can ask for additional evaluators. Right? You can do so at any point in your driver, in any class. It's not required that it is in some sort of main or that it happens at the beginning of your computation. You can always ask for more evaluators. This is important, for example, when you see load spikes and you want to ask for some more machines to act on them, or when you see that machines fail and you want to run stuff on different machines. Then the start handler uses this guy. Oh, we don't have the. One second. Why is it not moving? I can move the cursor, but I can't scroll. This is awkward. Okay, somehow we don't see the content of the start handler. One second. Presentation. I was looking for this one. Okay. There we go. So the start handler then uses this requester to just ask for one evaluator of only 64 megabytes of memory. Right? And then that's it. That's all that the start handler ever will do. It will just ask for that one evaluator that we want to run on. In other applications, it might do a lot more. Right? It might figure out where's my data, which machines do I want, all of that stuff. But for Hello Reef, that's all it needs to do. And then in the allocation handler, all we do is we do create a context configuration. In this case, the context is empty. It just has a name. And we create a task configuration where we give the task a name again. This is again for identification. Reef itself doesn't depend on what kind of name you give here. You can always use the same. It will just make it nearly impossible for you to read your own log files, because they will all be called the same, and it's kind of tricky. Then we set the task to hello task, and we submit this context and task for execution on the evaluator. And that's all there is in the Hello Reef driver. There's this try catch around here where we catch the bind exception. Bind exception is thrown by Tang whenever anything goes wrong with building a configuration. So when you try to set a value that's already set, when you forget to set a value that is required, all of those will trigger a bind exception. They shouldn't happen at runtime, right? But it's incredibly useful at debugging and development time to have them. And in Reef, you will often find this kind of, when we catch it, we immediately bail on the whole application by throwing a runtime exception. Okay. Let me go back to this and quickly do a summary. Okay, so what we've seen yesterday and today combined is the simplest program that you can run on Reef, which is Hello Reef. Get a single driver that goes ahead and asks for a single evaluator, submits a single task to that, and that task only printing one thing. We went through compiling Reef. We went through running all of this on both the local and the HD Insight runtime. And again, I'll be in the other room for the next hour to help those where it didn't work on the HD Insight runtime. I hope that I gave you a glimpse of why Tang and why it's cool and what it does for you. If you're not convinced, that's okay. You still have to live with it for Reef. And I showed you how we do context and why they are useful. With that, I just want to say what we do tomorrow. Tomorrow we actually do some machine learning. We start by introducing the group communication primitives that we have in Reef for broadcast and reuse. And then we will look at a very simple learning algorithm, namely batch gradient descent, with a fixed learning rate and a fixed number of iterations. So nothing that you would do in practice, but pretty close to actual machine learning. Thanks. Oh, and someone borrowed me a USB stick yesterday. If you want it back, please come to me.